Assalamualaikum. My name is Muhammad Haziq bin Muhammad Nasir. I'm from Group 8C. Today, I will explain to you about root locus. What is root locus? Root locus is a graphical technique used for analyzing the behavior of a control system. It shows the movement of the system's pole in the complex plane as a parameter, typically a gain. The plot starts from the system's open loop poles and ends at its zeros. It also provides insights into the stability and transient response characteristics of the system. By studying the root locus plot, we can determine the stability of the system. Besides that, it helps in selecting parameter values that yield stable behavior. It is also a valuable tool for analyzing and optimizing feedback control system. Lastly, the plot is particularly useful for visualizing pole movement and understanding system behavior. Next, the advantages of root locus compared to Nyquist. The root locus plot provides a visual representation of how the system's pole move as the parameter is varied. It allows engineer to observe the trajectory of the poles in the complex plane, giving a clear picture of how the system's behavior changes with different parameter values. The root locus method makes stability analysis straightforward. By examining the plot, engineers can easily determine the regions of the parameter values that result in stable or unstable behavior. The root locus also offers valuable insight for control system design. Engineers can use the plot to identify parameters values that meet specific design requirements. By analyzing the plot, they can optimize the system's performance by selecting appropriate parameter values. The root locus method provides an intuitive understanding of how the system behaves in response to parameter variations. By visualizing the pole movement, engineers can know the cause-effect relationship between parameter changes and resulting changes in system dynamics. This coding demonstrates the use of the root locus method for control system analysis and design. Variable S represents the Laplace variable in the complex frequency domain. G is the open loop transfer function. The gain parameter K is set to 2. SYS is the closed loop system defined by feedback. Then plot the root locus diagram for G. This is the complete root locus plot of a control system resulted from the coding. And this is a closed loop system. Moving on to the transfer function of the system, let's consider the block diagram for both open loop and closed loop systems. The key difference between the two is the presence of feedback in the closed loop configuration. The open loop transfer function represents the system without any feedback. The block diagram consists of a transfer function that describes the plant or process being controlled. The closed loop transfer function incorporates feedback in the system. The block diagram includes a feedback loop where the output is fed back and compared to the desired input. It's important to note that the feedback loop in the closed loop system affects the overall system dynamics, leading to different stability and performance characteristics compared to the open loop system. Okay, next, the Matlab code indicates that the breakaway point for the system is -0.785. This breakaway point represents a critical value of the gain parameter at which the poles of the closed loop system begin to separate on the root locus plot. It signifies a significant change in the system's stability and behavior as the gain parameter is varied. Next, the Matlab code shows that the critical value for the gain parameter, denoted as K critical, is 30. This value agrees with the calculated result from the Ruth stability analysis, indicating a significant point where the system undergoes a noticeable change in its stability performance. Next, this plot represents the system's response when the critical value of the gain parameter K critical is set to 30. The maximum natural frequency of the system is determined to be 2.45, which aligns with the manual calculation mentioned in the previous slide. The agreement between the plot and the manual calculation reinforce the accuracy of the analysis performed.
Question A. Describe briefly in graphical form the stability criterion in Bode diagram. The answer is Bode plot stability criterion is a mathematical tool that engineers use to analyze the stability of control system. The criterion considers both the gain and phase characteristic of the system and provide a quantitative measure of the system stability. The Bode plot stability criterion is an essential tool for engineers who work on design, analysis, and troubleshooting of control systems. The Bode plot stability criterion introduces two critical measures of stability, which is the gain margin and the phase margin. The gain margin is the amount of additional gain that can be added to the system without causing instability, while the phase margin is the amount of additional phase shift that can be introduced without causing instability. These margins are important because they provide an indication on how close the system is to instability. A small gain margin or phase margin indicates that the system is more likely to become unstable if any additional gain or phase shift is added. Next, it is important to note that the gain and phase margin are related to each other. As the gain margin decreases, the phase margin also tends to decrease. This means that a system with a small gain margin is also likely to have a small phase margin. The stability of the control system based on the relation between gain margin and phase margin, which is if both the gain margin and the phase margin are positive, then the control system is stable. If the gain margin or the phase margin are negative, then the control system is unstable. The Bode plot stability criterion is a powerful tool for control system engineers. Its practical applications are numerous, and it is an essential tool for designing stable control system, troubleshooting unstable system, and improving system performance.
Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Hisham, and right now I will continue with question 3b, which is to sketch the open loop Bode asymptotic plot and obtain the gain margin and phase margin of the system and comment on the stability of the system. So given in the block diagram is the equation, which is 30 in bracket s plus 8 over s in bracket s plus 2 in bracket s plus 4. So I need to expand the equation, and the new equation obtained is as in the coding, which is for numerator, which is we have 30s plus 240 over the numerator s cubed plus 6s squared plus 8s plus 0. So this is the new equation obtained, and then I need to plot the Bode plot in this Matlab by giving instruction Bode in bracket GH and between margin in bracket GH. So the graph obtained is as in this picture at the above. I can say this graph is accurate because the value obtained is the same as the given box at the below. So as you can see at omega 0.2, which is at the frequency 0.2, I obtained the same value for magnitude, and for phase diagram for omega 0.8, the same value obtained for frequency, for magnitude and for phase diagram, and same goes to the other omega values. So in this graph, to obtain the gain margin and phase margin, it already stated at the graph, which is the gain margin is negative 1.94 decibel, at 5.66 radians per second. Meanwhile, for phase margin, it is negative 1.64 degree at 6.25 radian per second. So, to know whether this graph is stable or not, we need to look at the gain margin and phase margin of the system. So when the gain margin is lesser than the phase margin, or we can say that WPC is lesser than WGC, the graph is unstable. So for this experiment, we can conclude that this graph is unstable because the GM is lesser than the PM of the system. So that's all for me. Thank you, and we'll continue with the next experiment.
Hello and Assalamualaikum. So for the next section, we're gonna talk about the lab assignment Nyquist plot.
Hello, I'm Abdul Muiz. So here we are gonna talk about the Nyquist plot. What is the Nyquist plot? Basically, it is a graphical representation that used in a control system engineering and in a signal processing. It is used to analyze the stability and frequency response characteristics of a system. Theoretically, Nyquist plot is named after the Swedish engineer, which is Harry Nyquist. Let's look at the application of the Nyquist plot. The first and foremost is a stability analysis. The Nyquist plot is used to analyze the stability of control systems. For example, by examining the encirclements of the point -1, 0 in the complex plane, the Nyquist plot can determine the number of unstable poles of the system. Furthermore, the Nyquist plot is used in a controller design. So by analyzing the Nyquist plot, engineers can determine the necessary modifications to the system's frequency response to achieve desired performance characteristics such as stability, response speed, and disturbance rejection. The last application of Nyquist plot is frequency response analysis. As we know that Nyquist plot provide visual representation of the frequency response, so by looking at the shape and behavior of the plot, engineers can understand how the system responds to different frequencies. This analysis helps in identifying resonant frequencies, system bandwidth, and frequency-dependent effects such as phase lag or lead.
Hello, my name is Nur Syahira binti Masya. So for the next is solution. As we required, we need to solve the question using the Matlab or Simulink. So for the first question, based on your understanding, plot the Nyquist diagram of the system if K equals to 1. So for the transfer function for the open loop, we get K over S power of 3 plus 0.5 S power of 2 plus S. Okay, to solve the question, so this is the coding of the Matlab, and then we can get the Nyquist diagram. So in the Nyquist diagram, we can know the frequency which stand for the omega, and the imaginary axis and the real axis. Okay, next, for the next question, determine the value of K so that phase margin PM is 60 degree. So to solve the question, the magnitude equation can be derived as this formula, and then to solve this formula, we need to use two formula, which is the phase angle equation and the phase margin equation. So when we solve it, we can get the omega equals to 0.6 radian per second. So at this particular frequency, the magnitude of the G is equals to unity, which when we solve it, we can get the K equals to 0.43. So we insert the value of K, which is 0.43, and then we will get this Nyquist diagram. So as the question is, we need to determine the value of K when the phase margin is 60 degree. Next, the third question. What will be the gain margin at this condition? So to solve the question, the gain margin formula is this formula, and then to solve the gain margin formula, we need to use the first crossover frequency equation. So when we solve the equation, we can get the gain margin is equal to infinity, which means that the gain margin is unstable system. So in the Matlab, we use this coding, and then we can get this Nyquist diagram. So as you can observe in the diagram, the path never cross the real axis, which is at the red point. The path never cross the real axis in the left half plane. So which means that the gain margin is infinite. Okay, next, the last question. To obtain the range of k in ensuring the system stability, so we use the roots method, and the characteristic equation of the closed loop transfer function is given by s power of 3 plus 0.5 s power of 2 plus s plus k equal to 0. So we use the roots method table, and then we determine the determinant of this equation is by this formula. So to ensure the system stability, so we solve it, we can get the k is range between 0 to 0.5. So we use the k equal to 0.4 and then insert it in the Matlab code, and then we can get the Nyquist diagram. So as you can see, the gain margin is the Nyquist diagram is stable system, because the diagram shows that the path cross the real axis in the left half plane. So that's all from us. Thank you. I hope you learned something new.